Hertz contact is a continuum elasticity result. Cundall-Strack is different. It is a soft contact penalty model used in the discrete element method. In this video we derive the contact geometry, normal spring, tangential memory, Coulomb cap, forces, torques, energy, timestep restriction, and stress averaging. DEM repeatedly maps positions and velocities to contacts, contact forces, torques, and then new particle motion. The Cundall-Strack law applies the local mechanical rule inside this loop. The normal force is instantaneous, but the tangential force remembers previous tangential displacement while the contact sticks. The model begins with assumptions. The particles are treated as rigid bodies, but a small numerical overlap is allowed. Contact compliance is lumped into springs. The stiffnesses Kn and Kt have units of force per length. They are not the particle Young's modulus or shear modulus. The center distance is d. The contact normal is the unit vector from particle 1 to particle 2. The scalar overlap is r1 plus r2 minus d. A contact is active only when this overlap is positive. If the overlap is zero and negative, both the normal and tangential contact forces vanish. For small overlap, the contact point is taken on the line of centers. The lever arms from each particle center to the contact point are needed for torque. Normal force passes through the centers for spheres, but tangential force acts at the contact point and creates a moment. The velocity at the contact point includes both translation and rotation. Compute the contact point velocity on each body. Then subtract particle 1 from particle 2. This relative contact velocity is the input for the normal and tangential velocity split. Project the relative velocity onto the normal direction and subtract that projection. The remainder lies in the tangent plane. Particle spin contributes to tangential motion. But for spheres it does not change the center distance and therefore does not directly enter the overlap rate. The normal law is the defining penalty relation. Normal force equals normal stiffness times overlap and exists only in compression. With the normal pointing from particle 1 to particle 2, the force on particle 1 is opposite the normal and the force on particle 2 is along the normal. If each particle contributes compliance at the contact, those compliances act in series. The same contact force passes through both contributions and their displacements add. Therefore inverse stiffnesses add. For two identical per particle stiffnesses, the effective contact stiffness is 1/2 of the per particle value. The normal force depends on the current overlap. The tangential force depends on the accumulated elastic tangential displacement while the contact sticks. Each timestep adds tangential velocity times timestep to the rotated old history. Then converts that stored displacement into a trial restoring force. The tangential spring must live in the current contact plane. When the contact normal rotates, the old history vector must be moved into the new plane. The minimum consistent operation is projection. Remove the component parallel to the current normal so that the stored vector remains tangential. The sign convention must be fixed before writing the vector equations. Here the relative contact velocity is contact point 2 relative to contact point 1. The restoring tangential force on particle 2 is therefore minus Kt times the stored tangential displacement. The force on particle 1 is the negative of that force. The tangential force cannot grow indefinitely. Its magnitude is capped by the microscopic interparticle friction coefficient times the normal force. Equivalently, the coefficient is the tangent of the contact friction angle. This contact friction angle is not automatically the macroscopic friction angle of the granular. Assembly. The tangential update is an elastic predictor followed by a Coulomb corrector. First, compute the trial tangential displacement and trial force. If the trial force is inside the friction circle, the contact sticks. If it is outside, project the force to the Coulomb boundary and reset the stored elastic displacement consistently. The total force is the sum of the normal and tangential parts. With the convention used here, the tangential force on particle 1 is minus the tangential force on particle 2. The total forces are therefore exactly equal and opposite. So Newton's third law is satisfied at each contact. For ideal spheres, the normal force acts along the line of centers and produces no torque. The tangential force acts at the contact point and has a moment arm about each center. That moment changes the particle spin through the angular equation of motion. After the contact forces and torques are known, particle translation and rotation follow Newton-Euler dynamics. The translational acceleration comes from the total force, and the angular acceleration comes from the total torque. DEM then advances the particles and repeats the contact loop. The explicit method is efficient because it avoids a global matrix solve. But it is only conditionally stable. The stiffest local normal contact can be approximated as a reduced mass connected to a linear spring. Its natural frequency controls the stable timestep scale. Apply central differences to the local normal oscillator. The discrete update has a characteristic polynomial. Bounded oscillations require the roots to remain on or inside the unit circle, giving omega naught times delta t less than or equal to 2. Practical DEM uses a smaller safety factor. Damping must not be hidden inside the stiffness. Some simulations use numerical damping to relax quasi-static packings. Others use a dishpot in parallel with the normal spring. For a non-adhesive contact, the normal force must be clamped so that unloading does not create artificial tension. For a linear spring dishpot collision, the damping ratio is Cn divided by 2 square root of reduced mass times normal stiffness. The coefficient of restitution follows from the damped oscillator. This is mathematically clean but physically limited because it predicts velocity independent. Restitution. The normal spring stores 1/2 kn delta n squared. During sticking, the tangential spring stores 1/2 kt times the squared tangential displacement. During sliding, Coulomb friction dissipates work. These are linear spring energy expressions, not Hertzian contact energy. Hertz contact has a finite contact radius and a pressure distribution. Cundall-Strack does not. It applies a point force between rigid particles with lumped compliance. Therefore a Hertz contact radius, local pressure field, and maximum pressure are not defined unless an extra artificial coarse graining area is introduced. Cundall-Strack has no Hertzian stress field inside a grain, but an assembly stress can be computed by volume averaging contact forces and branch vectors. This Love-Weber type expression converts a discrete force network into a continuum average stress over a representative volume. For an isotropic monodisperse packing, the mean normal contact force follows from the average stress, particle number density, contact density, and a branch length of about 2 radii. The result scales linearly with the confining stress magnitude and quadratically with particle radius. At a single Cundall-Strack contact, the normal stiffness is constant and force is linear in overlap. Any pressure dependence in the macroscopic response of a packing does not come from Hertzian nonlinear contact elasticity. It comes from the changing average overlap, coordination number, fabric, and contact network structure. For two identical particles, the reduced mass is 1/2 of the particle mass. The branch length is approximately 2 radii. And equal per particle contact compliances give 1/2 of the per particle stiffness as the effective contact stiffness. These simplifications are useful for hand checks and timestep estimates. The operational algorithm is short. Detect the contact from geometry. Predict the tangential elastic response from the current relative velocity and stored history. Correct the tangential force if the Coulomb cap is exceeded. Then sum forces and torques and integrate the particle motion explicitly. The common errors are not cosmetic. They change the physics. The stiffnesses are not continuum moduli. Hertz pressure formulas do not belong inside a pure Cundall-Strack contact. Tangential history must be kept in the current contact plane. The force sign convention must be fixed before equations are written. Cundall-Strack is valuable because it is simple, local, and computationally cheap, but its claims must be limited. It is not a Hertz derivation. It has no intrinsic contact pressure distribution. Damping and rolling resistance are extra modeling choices. And the stiffness parameters require calibration for the physical question being asked. The full model reduces to a compact set of equations. Geometry gives overlap in normal direction. Linear springs give normal and tangential trial forces. The Coulomb cap determines sticking or sliding. Tangential force creates torque. Particle motion follows Newton-Euler equations. And assembly stress follows a force branch average. The final check is conceptual. Cundall-Strack is a linear soft contact DEM law with tangential memory and a Coulomb cap. Hertz theory is a separate nonlinear continuum contact law. Mixing their symbols without changing the contact model creates a false derivation.